everyone. I hope you're doing great on this wonderful BD Escape Day. As you may know, this is the showcase plan, and we're here to solve site reliability engineering, or SRE for short. Now you can think of SRE as operations and resilience done by devs, and we want to take you on a journey which follows a dev's path into the world of SRE. Now our goal at the end of this weird and wonderful journey is to have a better understanding of the practice of building anti-fragile systems. Let's be honest, none of us like dealing with production incidents or prod support when something goes wrong. Whether you're a dev, analyst, team lead, manager, or fill any other role in the BBD community, you're guaranteed to have heard of or experienced some painful war room scenarios. Now, we can't make that pain go away completely, but by focusing on building resilient systems from the start, we can go a long way to incidents and reducing the pain when they do happen. So, it works on my machine. Raise your hand if you've ever heard the statement, or more likely said it yourself. Of course it works on your machine. It always does, right? It's not like you just spent the past 4 hours making sure of that before showing it to anyone. Now, this is okay to laugh at because it's a pretty common occurrence, but let's take a moment to think about the implications of this statement. Writing code and testing it locally is one thing, but running code in production is a completely different ballgame. So let's take a step back for a moment and think about a more traditional ops workflow. As a dev, you write code to satisfy some business need. You verify the code locally through units and integration testing. You then toss the code over the wall for the ops team to build and deploy and proceed to forget the code exists. This is clearly an issue, since the team responsible for writing the code is completely separate from the team responsible for building it, deploying it, and managing the day-to operations.
So those of you who might be paying attention or familiar with this, you might be thinking this is going to be another DevOps talk, right? Isn't what DevOps was supposed to solve, bringing these silos together? So to answer that question, let's step back a bit and define what DevOps does. Right now, we might think what a DevOps engineer these days is a guy that runs around configuring CI pipelines, delivering, testing, and all of that good stuff. But actually, that's not quite DevOps. The same way as doing Scrum doesn't mean you're agile. Right? Because as Jason mentioned, we had developers writing code and delivering software, but not necessarily ever knowing how it was going to run in production. Then we had these ops teams, right, who were focused on running these things on production. Problem there is they have two competing concerns. One team values stability above all else, the other team wants to deliver. And often they come together. So this is where DevOps emerged more as a culture or a set of practices or principles with a goal to eliminate those silos, right, through practices. But the core problem here is DevOps doesn't actually prescribe a way to achieve this. It doesn't say this is how you get from here to here. It just says that this is what we want to achieve, right? So it's also partly why some DevOps initiatives do fail, because there's no roadmap on the way forward to this. And it's very much concerned with the development lifecycle, from inception to getting something everywhere. So now let's enter SRE into the conversation. SRE developed, as a lot of things do, out of Google at around the 2000s. Independent, but simultaneously as the DevOps movement, right? Because the DevOps cycle, if you think about it, focuses inception, moving forward, development, delivery into ops, right? However, these core-enabled DevOps teams, engineers, sometimes don't still have the purview or control over production in some environments, or the skill sets. Now that's where SRE comes in. SRE is a team of engineers who views the system from production down, not from inception forward, right? And what it does is it actually views this from a software development mindset. We're engineers, we're going to solve these problems using software, right? And thus, it's called 50-50 job. An SRE engineer's job, 50% of the time is dealing with the tactical stuff, toils, incidents, investigations, improvements. But importantly, the other 50% of the time, what we're doing is using software, building software to automate all of these problems away as we see them come and drive value that way, right? We're actively involved in engineering. So we're engineering value through operations. It's famously quoted as saying, what happens when you give a software engineer the job of being ops? They're going to look to write code to make ops better. That's a fundamental difference when viewing SRE from an ops point of view and also from a DevOps point of view. I like the way Bradley Knapp from IBM Cloud puts it. When you want to know how your system was intended to run, designed to run, and what problem it was going to solve, ask your DevOps or core dev teams. If you want to know what your system is actually doing, ask your SRE engineers. So as I mentioned, SRE now is more prescriptive. It does embody some of the DevOps principles because they evolved together, right? But we can see that it's more prescriptive in the areas of concern that a DevOps, that a SRE engineering team might go about investigating. These various pillars we're going to try and cover today are monitoring and observability, reliability and resilience, elimination of toil and capacity, and release management. I'm going to throw you back to Jason so he can dive in a bit into the monitoring and observability pillar.
Yeah, so let's start off with our first pillar, monitoring and observability, which focuses on gaining insight into your system with the aim of rapid and preemptive issue detection. Monitoring is what you do after a system is observable. This makes observability one of the most important characteristics of an SRE implementation. Observability originates from control theory, and it's a measure of how well you can determine your system's internal states from its external outputs. Monitoring, on the other hand, needs to answer two simple questions: what's broken and why? Monitoring enables you to watch and understand your system with the aim of detecting a known set of failure modes. Now, in our new stack, which we might call it, it's typical to have workloads that are cloud native and distributed in nature, consisting of microservices. For better or worse, we can't truly monitor this new stack using legacy methods, which focus on detecting predictable failures. We can only truly monitor our new stack once it's observable. Now that we've looked at the difference between monitoring and observability, let's examine two monitoring strategies: black box and white box monitoring. SRE combines heavy use of white box monitoring with modest but critical use of black box monitoring. Black box monitoring is symptom-oriented and focuses on determining when there's an active problem in your system. White box monitoring, on the other hand, requires the ability to inspect the innards of your system and facilitates detection of a wider range of issues, such as imminent problems or failures masked by retries. White box monitoring throughout a system is crucial. For example, say you were to have a web server being slow on database-heavy requests. You would need two pieces of information. Firstly, how slow does the web server perceive the database to be? Secondly, how slow does the database believe itself to be? Without this information, you can't possibly distinguish between a database that's actually slow and network issues between your web server and your database. So let's take a look at one of our services running in production. Well, that's kind of awkward, right? You can't really tell from this video, but one of our customers is having serious issues while using our system. It'd be great if one of our engineers had some way of knowing what went wrong. This is where logging comes in. Logging is the most basic level of monitoring and also the most granular. Log data represents an event and it tells a story of what's happened. Now, we hope that all of our engineers are already implementing good logging practices, most of which can be achieved by using a good logging library. So let's not labor on that point. When it comes to logging, there are factors that SREs are concerned with over and above these good practices. SREs are concerned with the speed of logging. Having actions reflected in your logs in a timely manner is crucial, otherwise we might make incorrect assumptions or be unable to tie cause and effect together. It's also important to consider the amount of noise in logs. Too many logs can be as bad as too little in some scenarios. In our new stack, it's common to see an explosion of logs due to the ephemeral and polyglot nature of our workloads. To mitigate this, structured logging with configurable levels has become vital. This allows SREs to enhance log ingestion pipelines, as well as indexing, metric collection, analysis, and correlation. The most important part here is that SREs build tooling and leverage known tooling to codify these best practices, such that users of the platform can adopt them easily and with minimal effort. So let's check back in on our production service, now with some logging enabled. As soon as an error occurs, we can see the details in our logs on your left. In this case, our stack trace shows that we're getting a 500 from our service. It's a bit verbose, but it will help us diagnose the issue. Now, let's move on from logging to metrics. The difference in collection between the two lies in the fact that logs are collected any time an event occurs, while metrics are collected on an interval in a probe fashion. The time series nature of metrics makes them perfect for representation on graphs, such as gauges, counters, and timers. Now, the natural question may arise: do you need both logs and metrics? Let's answer that with an example. Say you were to suddenly start having issues on one of your servers. You could look back at the logs, but the problem may be that you don't really know where the issue started in all the noise. You look at your metrics and you notice that memory utilization is fairly consistent, until you spot a sudden spike. This tells you that something's wrong, but it doesn't really give you all of the necessary details. Bringing logs and metrics together can provide much more clarity. During the spike in memory utilization, you may notice some unusual log entries, which finally leads you to the root cause of the problem. When considering which metrics to collect, SRE identifies 4 golden signals. These are the key areas of focus when it comes to making a system observable. The first signal of interest is latency, which is a measure of how long it takes to service a request. It's important to distinguish between the latency of successful and failed requests, since the only thing worse than an error is a slow one. The next signal of interest is traffic, which is a measure of the demand being placed on your system. This is generally measured in some high-level system-specific metric, which would typically be HTTP requests for most web-based applications. Errors are, of course, an extremely important signal, since they represent the rate of requests that fail. Failures may be explicit or implicit. For example, compare a standard HTTP 500 response with a 200 response that returns the incorrect content. Failures can even be measured on policy violations. If we commit to a response time of 1 second, any request that takes longer is actually an error. Now, a final signal of interest is saturation, which is a measure of how full your system is. It emphasizes the resources that are most constrained, but it can be difficult to measure directly. Latency increases are often a leading indicator of impending saturation. Tracking these 4 golden signals is an important first step towards a comprehensive monitoring stack. So if we take another look at our production service, now with some metrics enabled, we can see that we have an error occurring. As soon as the metric updates, we can see that there's been an error. The details provided with the metric allow us to hone in on the problematic service and time frame. So as we saw, having metrics in our system is an important step towards anti-fragility. But now we need to consider how we can make them work for us. This is where we get to alerts. Based on the metrics we collect, we can send an alert to the appropriate person, letting them know that something has gone wrong. We consider 3 categories of alerts. Reactive alerting focuses on determining when there's a problem in our system right now. Well, a customer has just experienced an error. Proactive alerting focuses on determining when there may be an issue in future, and we'll touch on that point more a little bit later. Finally, investigative alerts focus on determining when our system is in some kind of unusual state. The state might not be causing issues right now, but there may be the potential for future issues to arise due to it. The most important point here is that we finally have the ability to know that something has gone wrong before an end user contacts us. So the alerts in our production service clearly highlight what I've just mentioned. As soon as an error occurs, we're notified. The details provided with the alert allow us to see what's gone wrong without having to dig into the logs or read the raw metrics. Great, so we've got alerts in our system, and this is a great way to know when something has gone wrong. But we need to consider how we can reduce fatigue associated with reactive alerts by moving towards a more proactive alerting approach. We define 3 aspects of interest. First up, a service level indicator is a carefully defined quantitative measure of some aspect of the level of service provided. If you're not monitoring something, you cannot possibly have an SLI for it. As an example, an SLI might be the rate of successful HTTP requests, which we could measure by taking the number of 500 responses over the total number of requests. Next up, we have a service level objective. This is simply a target value or percentage of an SLI over a given time frame. It's a measure of the level of reliability we'd like to offer to users of our service. Going back to our example, an SLO might be that we want a success rate of 99.9%, which means that 1 in every 1,000 requests can fail with a 500. Finally, we have a service level agreement. This is an acknowledgement that we can't avoid all issues, and it's a measure of the level of reliability users of our service can expect. It's typically more lenient than our SLO, which is a target. In our example, we might have an SLA of 99%. This means that 1 in every 100 requests can fail, which is much more lenient than our SLO. Now let's see how we can feed all of this back into our alerts. Since we acknowledge that failure is inevitable, we instead define error budgets. An error budget is a clear objective metric which determines how unreliable a service can be within a given time frame. This is clearly linked to our SLO. We also have the concept of a burn rate, which can be calculated by taking the percentage of your error budget that's been consumed over the percentage of your SLO time period which has been consumed. You can see burn rate represented by the gradients on the graph. Okay, right, so we can use burn rates to predict SLO breaches. As a concrete example, consider our HTTP request scenario with an SLO window of 7 days. Our error budget is 99.9%, which means, our SLO is 99.9%, which means we have an error budget of 0.1%. If we were to have an error rate of just 0.005% per hour, we would end up with 8.4 times the number of allowable errors at the end of our 7-day window. Predictions like these serve as the base idea for a good alerting system. We now have the ability on a service-by-service basis to predict when we might breach our SLO and alert accordingly. In this way, we reduce alert fatigue by only alerting on failures that truly threaten our acceptable levels of service. Great, so we've got our fancy proactive alerting system, but what good is it without some accompanying dashboards? As we saw earlier, metrics are great for representation on graphs. In the same way, we can represent our SLOs, error budgets, and burn rates, since they're all calculated based on metrics. Visualizations provide a way to rapidly turn wealths of metric data into useful information. The dashboard of our production service highlights the usefulness of visualizations, as we can quickly determine when something has gone wrong. Okay, right, so now one final part of a good monitoring system is instrumentation. Microservice architectures have grown increasingly more popular, and for good reason, but they do bring a unique set of challenges when it comes to monitoring and observability. Not only do we want to be able to monitor each microservice individually, but we want to be able to track a request as it flows through the system and determine where something has gone wrong. Distributed tracing enables this by using traces to represent requests in the system. Traces consist of multiple spans, and each span represents some kind of system request interaction, such as communication with a data store or processing by a microservice. Spans indicate errors along with relevant details, as well as system latency, which can be represented by the length of the span. So let's consolidate all of our new knowledge and see how an SRE would tackle a potential SLO breach. Remember, our system should not alert us unless our error budget is at risk of being consumed during the SLO time period. First, we'd prioritize the issue based on the burn rate as well as case-specific details. We'd start at our dashboard to figure out what the issue is and where it's coming from. Next, we'd obtain relevant details from our metrics and tracing. Only if we don't get sufficient details from our metrics and instrumentation would we search the logs for the root cause. Of course, it's always better if we don't have to get to this process in the first place.
Thanks, Jay. So Jay's covered some high-level topics around monitoring and observability. So I'm going to talk more now about reliability and resilience. Because now that we know how to monitor, we know that we might fail, what can we do about when we fail, right? So I want to start off with maybe explaining anti-fragility or trying to define it. So anti-fragility is beyond resilience or robustness. The resilience shocks and stays the same. Anti-fragile gets better. So I'm going to try to put this in a system-specific way. Let's say what fragile would be to a system. This is a system that is fundamentally at risk of going down and causing a financial impact. A resilient system is a system that avoids cascading failure and can recover itself from an event or an unknown event. Robust systems are slightly better than that, and they can attempt to repel events. Now, what we're chasing actually at the end of the day is anti-fragile systems, where a system mutates itself due to events to maintain a fit for purpose nature. So it actually changes itself in reaction to what's happening around it. Now, as Jason mentioned, our systems are growing very distributed in nature. And I just want to highlight these 8 fallacies of distributed computing, such as bandwidth is infinite, latency is zero. I want to highlight these because not so much of what they are, but what they represent. These are things that can go wrong, right? We have to know that they can go wrong, and they do go wrong. And what's hidden inside of these things, fundamentally, what's hiding is what we all call a black swan event. Now, what is a black swan event? I really like this metaphor because it explains it nice in my head, and it says a turkey is fed for 1,000 or more days, every day, together with other turkeys that take pleasure in the comfort of their life. Then comes Thanksgiving. Being a turkey will not be so cool and all. Right? So this is illustrating a black swan event, right? We think everything is happening, but something can happen that will fail us, and generally goes about happening. It manifests itself in the real world. Right? So what we do as SRE engineers is we accept this, right? We say things will fail. So how do we attempt to mitigate this, right? I like to think of the 5 Fs: fires, floods, fools, and fat fingers. Now, fires, I think of components of your system are on fire, portions of it, right? Floods are slightly bigger. We start losing availability zones. We lose network connectivity across the stand. Fools, well, those are people who just cowboy their way through things, make configuration changes, without good practice or good knowledge. And fat fingers, right? I'm guilty of this. We've all typed the wrong command in the wrong window at the wrong time, accidentally. So we have to consider all of these things together, right? And the fallacies that we know are going to come about, and we're going to have these problems. So what do we have to do? We have to anticipate this. We have to now induce this chaos, don't we? We have to surface it somehow so we can learn from it and then mitigate. And that's where the discipline of chaos engineering has come about recently. Right? Chaos engineering is a discipline upon which we experiment with our system in order for us to become more trusted or feel more comfortable that it can withstand turbulent conditions. So what we're actually doing is introducing chaos so we can learn from it. Now, the thing about chaos engineering is that we are creating chaos. And the thing about creating chaos is we need to know that we can stop it when we create it. Right? So to that end, chaos engineering kind of has some steps that is pretty well defined on how you would go about implementing a chaos engineering practice. First, we define step 1, which is defining a steady state behavior. So this would be an example. We know our system at a certain configuration of servers and config and replicas does 1,000 transactions per second with 0 errors. So that's our steady state behavior. We then hypothesize that this will continue to happen, that the world is good when we introduce some event. So we knock out an AZ, we knock out a network or something like that, right? Then importantly, as I mentioned, we define a stop condition because we're going to start chaos eventually. We want to stop it. Then, as Jason mentioned, we should already have all our SLIs and all our metrics to measure our experiments. First step, actually create the experiment to disprove our hypothesis. And then the final one is to automate this. So now we're actively going to go about causing chaos in our systems, right? If you're mature, we can do this on prod as well. We're testing our system through externally inducing chaos. Now, here's an example of some experiments we're running on one of our current infrastructures or platforms. Our experiments are constantly running, inducing partial outage and full outage, and we're expecting certain metrics to be met in recovery times, right? These are reported back to us on a continuous basis, so we can find out if we need to go investigate, see if something was wrong in order to improve our service going forward. The thing about chaos engineering is fundamentally what we're trying to do is trying to get ourselves from this illusion of control that because we've been running for a long time without any errors before, because we've run our predetermined end-to-end tests for a significant amount of time, that we actually are bulletproof. This is like the feeding of the turkeys, right? We don't want to get our heads into that zone. What we need to know is that there's Thanksgivings are coming, many Thanksgivings. So we want to surface that chaos in a controlled way, knowing that it's coming anyway, so we can learn from that and then make our systems recover from And that's how we eventually end up building our automations and our systems to eventually self-heal or mutate. In other words, become anti-fragile. Now, moving on from that leads us into elimination of toil. Right? Now, elimination of toil is basically, for all the engineers, using code to automate it. Automate all things. And you've heard a lot about automation, and you hear about and test automation, all these things. But fundamentally, this is almost at the core of an SRE's job, right? It's fundamentally coding automation. Now, why do we code automation? Fundamentally to get rid of toil. Now, toil is trouble, right? Now, let's speak about what toil is. Toil is not overhead. It's not stuff you don't like to do, right? It's not stuff you. If you do something once, it's not toil. If you do it twice, it's still not toil. If you find yourself doing it a lot and it's eating a lot of your time, now we're talking toil, right? And I'm wasting time when the machine could do it, right? So I'll speak to some characteristics of the type of work that could be considered toil. First, we have manual, right? Human runs a script every day, operations engineer. Good, we've got a script, but still requires human intervention. Could be done by a machine if it requires no human intuition. It's repetitive. We do this all the time, every day, every month, not once, twice, but over and over again. It's automatable. I could make a machine do this automatically. It has no enduring value. If these tasks that you repeat over and over again leave the system or the service in no better state than you found it, it has no enduring value. This machine can take it away, so we can then move on to doing things that are of value. It's tactical. So toil is normally interrupt driven. It interrupts you from your work, right? And it's reactive, right? Pages, alerts, things like that, right? We want to get to a position where we're strategic, right? And more responsive, ahead of the curve. Now, to that point, you're never going to get rid of all tactical nature. We're chasing the goal, but we can actively try and reduce all of those tactical issues so we can move on to become more proactive and less reactive to things. Finally, it scales up. Now, toil, the bigger your system gets, if you add toil, it tends to multiply on itself. It just grows and grows. Now, the thing about toil, it's the enemy of engineering value. Right? Toil is terrible. So we have to measure it, we have to track it, and we have to build stuff to get rid of it. Toil is bad because it stops us from actually doing good engineering. It's admin that we could give a machine to do. Now, I hate toil, but I'm just going to move a little bit aside here to mention that not all toil is bad, right? We've all been there. A couple of admin tasks is a good way to learn a system. Juniors start with admin tasks. It's also a sense of achievement, right? You get something done in a crazy world of maybe day two operations. But what I want to highlight is that you have to keep a good eye on it because toil in its nature is toxic, right? Any work that is toil is toxic. It's career stagnation. It slows the delivery because eventually as toil grows, there's less time for actual good engineering value, right? It's demoralizing and frankly, it's not cost effective because you're paying engineers to do things that machines can do at the end of the day. So it's important to track toil and use software engineering, literally coding, to solve these problems. And we'll touch more on the type of coding that an SRE engineer goes about to eliminate this type of toil. So that's me about toil and reliability. I'm going to hand you back to Jason so he can cover our last pillar, which is about capacity and release management.
Yes, so capacity and release management. One part of building reliable, efficient, scalable, and resilient systems that we can't ignore is capacity and cost. After all, most institutions and clients aren't Google with heaps of cash. Scale is much easier to contend with on an unlimited budget. So what many don't realize is that monitoring current capacity and costs can be a huge help in achieving these goals. As an SRE, you already collaborate with engineering, DevOps, and release engineers to build highly available and scalable systems, right? So why not engage with vendors to get a FinOps approach to cost? Using the proven automation techniques that Ricky mentioned, we can build cost-consciousness into our workflows. We then achieve our value, we deliver value to our clients and achieve our goal of efficient and scalable systems. Now, capacity planning. This is the art of forecasting the necessary resources to satisfy the demands of your system over time and ensuring that they're available. One approach to make this easier is the adoption of intent-based allocation. For example, instead of requesting 20 servers in regions A, B, and C to run our system, an intent-based specification might be to run our service with 3 nines of availability and latency of less than 200 milliseconds. This intent-based specification is much more flexible since it requires different numbers of resources at different times. But for companies that don't operate planet-scale infrastructure, this realistically requires running in the cloud. One final part of a stable system is a rapid and trusted release process. This process balances the releasing of new features against the reliability of the system, and generally entails providing tooling, automations, templates, and processes to adhere to some high-level standards. The release systems should support a high velocity while being able to adopt the continuous delivery and continuous deployment ideologies, as well as various deployment strategies, such as blue-green and canary releases. SREs work with DevOps to ensure that testing, building, packaging, and delivery are all automated and built into these processes from inception based on a shift-left principle. As part of their engagement on the release process, SREs are often responsible for identifying and implementing the most suitable deployment model for different teams.
Thanks, Jace, for wrapping up capacity and release management, and that covers fundamentally some of the pillars of SRE. Now, if you wanted to build an SRE practice or you wanted to get involved in SRE, we'll discuss maybe some models that we have seen or some models that have been adopted when you build an SRE team or an engineering team or whatever flavor you want to call them. First of all is the early engagement model. This is where you have SRE engineers, which all the institutional knowledge and specific set of skill sets that engage early with the core development teams or the DevOps enabled teams, right? So they can start building their production readiness criteria in from inception, right? So it's not retrofitted. Another model is a baseline support, a more scaled down, where the SRE engineers give the same advice, however, it's on an ad hoc basis where core dev or core engineering either engage the SRE team for advice or post-production launch to check that everything is okay. Or hand over the responsibility of a certain service to an SRE team, which is going to manage it. We have embedded SRE, which is basically almost like embedded DevOps. We have SRE engineer specifications inside of your teams, which are delivering in line with your teams. And finally, we have kind of like a kitchen sink SRE, which is basically SRE owns everything in production. Anything that is now in production is under the purview of SRE, monitoring, reactive, making better, automatable. It becomes owned by SRE. Now, when you have an SRE practice, because they're also software engineers at their core, their specializations might emerge depending on how big the client is, the system, the economies of scale. But generally, I'll highlight some common software engineering or specializations within SRE teams as engineers. Excuse me. So SRE tooling teams. You can think of these as engineers who are responsible for adopting or actual building tooling for their development or core team counterparts to leverage so that they can have all these cool reliability, automation things built in from inception. Right? We have SRE platform engineering, which is different. These are SRE teams who are now responsible for building capabilities that make their development counterparts easy to adopt, iterate quickly, right? While still having all these capabilities, all the good SRE practices inside of them. It's very different because now the SRE teams are not really dealing with the business services, more the underlying platform that the core dev teams are delivering their services upon. Then we have a reliability and standards practice team, one of my favorite. This is where SRE teams are responsible for all the SLOs, SLIs, breaches, production readiness criteria, reviews, and try and educate and push down approach. And then finally, I've seen a shared responsibility model, which is different, and basically the SRE team owns the production platform on which core engineering teams deliver their business functionality. That is very different because the engineers built this, are responsible for it, respond to it, and their clients are the core engineering teams who own their functional service entirely that go on top of this platform. But there are various flavors of these and various adoption because fundamentally SREs are engineers, right? We're coding 50% of our time to solve problems for engineering so they can move forward with our pillars always in our background because we want to get to anti-fragile systems. So I'll hand back so Jason can summarize some stuff that hopefully we have made visible to you during our journey.
Yeah, thanks, Ricky. So now that we have a better understanding of how we can set up an SRE engagement in our teams, let's focus on some key takeaways from our journey. First off, DevOps is not SRE. There are separate disciplines that work hand in hand, but their focus is on different components of the system. Another difference between SRE and DevOps is that SRE defines prescriptive pillars, namely monitoring and observability, reliability and resilience, eliminating toil, and capacity and release management. Almost all of the work that an SRE does falls under one of these pillars, with specific focus on automation and resilience wherever possible. At the end of the day, we want to work ourselves out of a job. Finally, the most important goal of an SRE is anti-fragility. All of the work we do is designed to ensure that systems can take care of themselves. Once we reach this point, we can look back and celebrate our success, but always beware of the black swan. Thank you.